As we move forward in this chapter, we continue to see more methods of proof and sometimes disproof. And so in this video, we'll be talking through proof by cases, counterexamples, and existence proofs. So again, you may want to watch this before you read these sections, or you may want to read the sections before watching the video, or maybe you want to do them sort of intermixed between each other. However you want to do it is fine, as long as it works for you. In this video, we will understand and apply three more methods of proof: proof by cases, counterexamples, and existence proofs. And we'll understand when one should apply these methods, and we'll look through a few examples of these proofs. As always, it's going to be crucial for you to be reading the book along with this. There's a lot more examples in the book and some more detail provided in different places in the book, so you're going to want to use both the videos and the book as resources. I just want to remind you of that. All right, we'll start by talking about proof by cases, and I want you to consider the following statement. Let n be an integer, then n squared minus n is even. So I want you to notice that if we want to prove this, we'd want to assume, so we would assume n is an integer and conclude, right, we'd want to show that n squared minus n is even. Now you might recognize this as one of those times when just assuming n is an integer, that's not going to give us any leverage. We don't really know what an arbitrary integer looks like. All we could do is say, hey, n's an integer. And it'd be hard to show n squared minus n is even just based off of that. And so you might think, oh, well, maybe we should try a contrapositive. But if we do, so that would be like trying to show this directly. We would do that. Or we could try the contrapositive. And what would we do there? We'd assume n squared minus n is odd and conclude that n is not an integer. So consider doing that again. So n squared minus n being odd, well, we could write n squared minus n as 2 times k plus 1, but that doesn't seem like a lot of leverage. And also, how would we conclude that something is not an integer? We haven't seen an example of that, and in fact, that's a very difficult thing to do, to conclude that something's not an integer. And so it seems like we're totally out of luck. We can't really do this directly, not enough leverage, and we can't do it by contrapositive, also not enough leverage. And so what would we do in a case like this? Well, what we can do is we can break it up into cases. So if we know that n is an integer, so assume n is an integer, we could go two directions with this. We know that n is either even, that's one possibility, or n is odd, that's the other possibility. So splitting it up, then we have leverage in either case, right? We can write n as 2k in the first case, and n as 2k plus 1 in the second case. And that gives us the leverage we need to then hopefully show n squared minus n is even. And so we'll end up proving two statements here, that if n is even, n squared minus 2n is even, and if n is odd, n squared minus 2n is even. And so in the case when directly you don't have enough leverage, contrapositive, don't have enough leverage, what you can do is go down to cases to break it up and hopefully get more leverage that way. Which cases you break it up into? Well, that depends on the statement. In this case, it seems pretty clear we should be considering even integers and odd integers, so splitting it up like that. And in fact, what we're doing is we're partitioning the integers into the evens and the odds. And then proving the statement is true on each part of the partition, and hence it must be true on the whole thing. That's the idea. So let's take a look at how to prove this in the next slide. So we're trying to prove the statement. We already said we're going to break it up into a couple cases. So let's start writing a proof for this. Proof. So when we do proof by cases, sometimes we can just write like case 1, n is even. In this case, let n be even, then we can use our leverage here, n equals 2k for some integer k. So n squared minus n in this case would look like 2k squared minus 2k, which is 4k squared minus 2k. And remember what we're trying to do. We're trying to show n squared minus n is even. And so we can factor out a 2 here. 2 times 2k squared minus k. And then I'll just write this last line, since 2k squared minus k is an integer, n squared minus n is even. So we wrote that n squared minus n as 2 times this integer, 2k squared minus k, and so we know it must be even. So that's the first case is done, right? If n is even, this holds. And so let's check the second case. So what if n is odd? So in this case, we'll let n be odd. Then n equals 2k plus 1 for some integer k. So what happens when we square it and subtract itself? So n squared minus n in this case would be 2k plus 1 squared minus 2k plus 1. And now we can expand this out and simplify. We get 4k squared plus 4k plus 1 minus 2k minus 1, which is simplifying now. We still have 4k squared. Now we have just plus 2k, and then the 1's cancel off. And we can see we can write that as 2 times 2k plus k. And then I'll just say over here, since 2k plus k is an integer, n squared minus n is also even. So we covered the case when n is even. We covered the case when n is odd. We know that any integer is either even or it's odd. And so it follows that we just proved it. And so I'll add a little tombstone to this. So that's the idea. We can always split it up. We can partition our set so that we get leverage in either part. Let's take a look at one more example of a proof by cases, and this will involve something called parity. So what is parity? If you haven't read through the chapter yet, you won't know, but parity just means that they're either both even or both odd. So we say two integers are of the same parity if they're both even or they are both odd. So two integers would have opposite parity if one is even and the other is odd. So that's the idea of parity. So let's take a look at an example of a proof involving something like this. So here we want to prove let m and n be two integers. Then 3m plus 5n is even if and only if m and n are of the same parity. So we need to show that m and n, we'd want to start with the assumption 3m plus 5n is even and show that m and n are either both even or they're both odd. And here we're doing an if and only if, and only if. And so we'd also have to show that if m and n are of the same parity, so if m and n are both even or they're both odd, then 3m plus 5n would be even. So this idea of, right, that's inherent to parity, either both even or both odd, that lends itself really well to this proof by cases, because we know there's two cases there for being of the same parity, both even or both odd. So that's sort of a big symbol, big signal that we'll need a proof by cases when we're dealing with parity like this. And this one, since it's an if and only if and we have two directions to go, this will actually have 4 cases to consider. So let me just talk through why that's true. So in the forward direction here, showing 3m plus 5n is even implies m and n are of the same parity. Well, you should see that we don't have enough leverage, that assuming 3m plus 5n is even, that's going to be not enough leverage. And so we should start by identifying that we'll do the forward direction by contrapositive. And so we'll start by assuming m and n are not of the same parity. That is, they're of opposite parity. And so we'll assume that m is even and n is odd, but then we'll also have to show that m is odd, or we'll also have to assume that m is odd and n is even. So there's a couple cases right there. So case 1, m even, n odd. Case 2 would be m odd, n even, and that's going to be for the forward direction, which is being done by contrapositive. And then for the backwards direction, we're going to be assuming m and n are of the same parity. Well, there's two things that could happen there. So case 3 will be m even, n even, or we could have them both being odd. Case 4, m odd and n odd. And so this is really going to boil down to 4 different cases. In the next slide, we'll prove this and we'll see how it all comes together. So I said in the last slide, we'll have 4 cases here. So first, let's just start proving this. We know 4 cases are going to show up. So proof, I'm going to do the forward direction first, forward direction, and I'll indicate I'm doing this by contrapositive, again, because we don't have enough leverage to do it directly. Contrapositive, contrapositive. Sorry about that. Contrapositive. Hopefully you know what I'm saying by contrapositive. And so we'll have 2 cases here. Case 1, we'll assume m is even and n is odd. And again, that's because we're going by contrapositive, so we're assuming the negation of this, that m and n are not of the same parity. Sorry, I underlined the wrong thing there. Right, we'll start by assuming m and n are not of the same parity. And then we'll show that 3m plus 5n is not even. We'll show that that's odd. So keep in mind our conclusion that we're trying to get to here is that 3m plus 5n is odd. Okay, so in this case, m is even and n is odd. We'll write m, I'll say then m equals 2k and n equals 2j plus 1. Again, keep in mind we need to use 2 different variables there, or 2 different constants rather, because we don't want any extra assumptions coming along. And I just want to say k and j are even, or are integers. So what happens here? 3m plus 5n, right? We want to make a statement about that. Now that we have our m and n written in these ways, we can combine them. So equals 3 times 2k plus 5 times 2j plus 1. And we can expand this out. So we have 6k plus 10j plus 1. Look at what we can do with this. We can do 2 times 3k plus 5j plus 1. And since 3k plus 5j is an integer, 2 times that plus 1 will be odd. So in conclusion, hence 3m plus 5n is odd. And that's what we wanted to show, right? We're going by contrapositive. We wanted to show the opposite of the hypothesis. Case 2 will be very similar to this one. Here we'll have m be odd and n be even. So I'm going to let you do case 2 on your own. Try that on your own. It works out very similarly, but I don't want to basically show the same thing again. And so that's the forward direction taken care of. the backwards direction, we would be assuming m and n are of the same parity, and we want to show 3m plus 5n is even. Notice in this case we do have some leverage, right? M and n being of the same parity. We can break that into the two cases. M and n are both even, where we'll have leverage, or M and n are both odd, where again we'll have leverage. So I'll just do one of these again. I'll work on case 3. How about? In this case we'll assume m even and n even. Then we can write m equals 2k. And n equals, say, 2j, where k and j are integers. And now we want to show that 3m plus 5n is even. Then 3m plus 5n is 3 times 2k plus 5 times 2j. 6k plus 10j, and we can factor 2 out so that we know it's even. So 3m plus 5n is even. Notice I'm sort of doing a little bit less detail with this one. I'm not writing out 3k plus 5j as an integer, therefore this thing is even. I'm just concluding right to it, and that's because we've already talked about those details. When you write your own proofs, you should include those, but I'm just sort of going a little bit quicker and not including every single detail of it. But still, there shouldn't be any logical jumps because we've already talked through those steps in logic. So I feel okay doing that. And so that takes care of that case. We know we'll have case 4 being m odd, n odd, and we'll want to show that 3m plus 5n is even there. And again, I'll let you do this on your own. It's not too different from what we already did, and I think you're probably getting enough practice with these even and odd stuff to be able to do that on your own at this point. So I'll go ahead and say end of proof. So we've already talked through proof by cases and seen a couple examples. Now we'll move on to counterexamples in existence. And these are actually very similar. It's really just two words for kind of the same thing. It's just one is for disproving something and one is for proving something. But we're really proving the same kind of statement in both. So you'll see what I mean in a second. So if you consider this statement for all x and s p of x, if I want to disprove that, if I want to show that that statement's false, then we need to show that the negation is true. The negation of this universal statement, remember universal statements switch to existential, so when we negate this it'll look like there exists x and s such that not p of x. And so counterexamples are really a method of disproof rather than a method of proof. But we know that disproving something is the same thing as proving its negation, and so disproving, proving, it's sort of the same thing. But you might see, we call this, when we find this x, such that not p of x holds, that's called a counterexample, when we're disproving a universal statement by providing a counterexample. That's what's going on here. And so, for example, you might see something like disprove the following statement. The product of two irrational numbers is irrational. So let's try and disprove this thing. So here we have a universal statement. It's saying for every two rational numbers, so I could write this as like for all x, y in, I'll use, we haven't used this notation before, but I'll use like a Roman numeral 2 or just like a boldface I to mean the set of irrational numbers. We could write this with set builder notation. Notice that the set of irrationals would be the set of all real numbers such that x is not rational. That would be a fine way to do this, or we could actually use some set operations, right? The irrational numbers are the real numbers minus the rational. So we could write this a few different ways, all meaning the same thing, just the irrational numbers. So for all x and y in the irrational numbers, x times y is also in the irrational numbers. So that's the statement that we want to disprove. So in order to disprove this, we need to show the opposite of that, and so we'll actually prove there exists a pair xy in the irrational numbers such that their product is not irrational, such that x times y is not irrational, which is the same thing as saying it's rational. So we want to take two irrational numbers. So this is the idea behind existence. We need to produce these things. We need to produce two irrational numbers whose product is rational, and that will serve to disprove this statement. So that's the idea here. That's what a counterexample is. And so let's do that. So I'll write here maybe disprove, disprove. Or maybe we'll say something like, I don't know, counterexample. So can you think of two irrational numbers, two numbers that aren't rational? We don't have a lot of examples of those, right? We know pi and e are irrational numbers, but also square root of 2 is irrational. I mentioned that in a previous video, and that's going to actually be our example here. Counterexample, let x and y be the same thing, and let them both be equal to square root of 2, right? Nowhere in here did I say that they couldn't be the same thing. This is still an example of two irrational numbers, right? Square root of 2 and square root of 2. It doesn't say distinct, and it doesn't say different, and so it's okay if they're both equal to each other. So let x and y both be square root of 2. Then I need to show that the product is rational. So then square root of 2 times square root of 2 is square root of 2 squared, or just 2, which we know is rational. And so that's a proof. Really, that's a counterexample to this universal statement. But we'll call it a proof, and so I'll write a box. So that's the idea here. So with counterexamples, we proved that a universal statement was false by showing that something existed which contradicted it, right? The idea with an existence proof is very similar. We're just going to prove that something exists. So this is sort of the other side of it if we just want to prove an existentially quantified statement. So if we want to prove something like there exists x and s such that p of x, well, we'll do that by providing this example. We'll show that we can find an x and s that satisfies p of x. So for example, maybe we can prove this statement. There exists rational numbers a and b such that a to the b is irrational. And remember, there exists, that's our key, that this is an existentially quantified statement. And so maybe we could rewrite this using symbols. There exists a and b that are rational such that a to the b is not rational, that it's irrational. And so instead of using that boldface I did in the last example, I'll just say not in the rationals. And so, right, this works the same way as counterexamples, except instead of disproving a universal statement, I'm proving an existential statement. And so let's prove this. Again, right, it's the same thing because I just need to come up with an example that works. So I need to find a and b rational numbers for which a to the b is not rational. Since square root of 2 is really like one of the three examples of irrational numbers we know, this is going to come up a lot. We're going to deal a lot with square root of 2. And in fact, in the last video of this chapter, we're going to prove that square root of 2 is irrational. So we're sort of using that a lot here, and we'll use it in this one. So one of our assumptions is just going to be, assume we know that square root of 2 is irrational. We'll just we'll take this for granted. Right now, we'll just take it for granted, and then later we'll prove it. And that'll be fun. And so what's our example here? Well, we need to find two rational numbers such that a to the b is not rational. Well, we know square root of 2 is not rational. Remember that square roots, maybe it's been a while since you've seen this, but remember that square root of 2, square root of anything, can be written as something to the 1/2, right? Use a fractional power. Square root of 2 is the same thing as 2 to the 1/2. And that's really the key observation here, is that fractional powers mean roots. And so what we can do here is let a equal 2 and b equal 1/2, then a to the b, right? I need to show that it really satisfies this condition that a to the b is not rational. A to the b is 2 to the 1/2, which is the same thing as square root of 2, which we're taking for granted is not rational, that it's irrational. And so that works as an existence proof. Again, we just need to provide an example for which this condition holds. And so that works here. So maybe I'm making this seem kind of easy to show an existence, right? We just need to come up with this example. But we're going to see a weird case here. Sometimes we can't provide an example to prove existence. That seems contradictory to what I've said. And it kind of is, but it's sort of not. Sometimes these existence proofs can be what's called non-constructive, which means I can't provide you an exact example that proves the existence, but instead I can give you a couple of options, and one of those options necessarily proves existence. So here's what I mean. We're going to take a look at this statement. There exist irrational numbers a and b such that a to the b is rational. Now that seems pretty far out there. Taking two irrational numbers, raising one to the other power, and then that ending up being rational. You might think this isn't true, but actually it is. And so we're going to prove this here. And this is an example of one of those weird cases I'm talking about where, well, we can't identify exactly what the numbers a and b are, but we'll give a couple of options and prove that one of those options has to work. So proof, I'm going to start by saying, what do I want to start by saying? I want to say consider a equals square root of 2 and b equals square root of 2, right? These two irrational numbers. We know a and b have to be irrational in order to prove this. So we'll consider square root of 2 and square root of 2. Then a to the b is equal to square root of 2 to the square root of 2. Now we can't say actually that this is rational yet. I'd like to conclude that that's rational, but it's actually not rational. We're not going to assume we know that. All we're going to assume is that, well, either square root of 2 to the square root of 2 is rational or it's irrational. Right? So we're kind of devolving now into two cases. We're using a proof by cases in this. So case 1, square root of 2 to the square root of 2 is rational. So if it turns out that this really is rational, then we're done. Right? We've given two irrational numbers, square root of 2 and square root of 2, such that square root of 2 to the square root of 2 is rational. Then we are done. So if it turns out square root of 2 to the square root of 2 is rational, we have nothing else to do. But maybe it's not rational. So case 2, what if square root of 2 to the square root of 2 is not rational? In this case, if it's not rational, it's an irrational number. And so what I'll do in that case, let a equals square root of 2 to the square root of 2, and b equal to square root of 2. This one's fun just because we get towers of these weird roots. And in this case, so if it's not rational, then I can use it for a, right? Because I need to come up with these two irrational numbers. So I'll use it for a. It's irrational. And I'll let b be square root of 2 again. And let's investigate a to the b. Then a to the b is, all right, so that's square root of 2 to the square root of 2, all raised to the square root of 2. Time to remember some properties of exponents. If I have a number, an exponent raised to another exponent like this, then I can multiply the two exponents together. This is the same thing as square root of 2 to the square root of 2 times square root of 2. Square root of 2 times square root of 2 is just 2, so this is square root of 2 squared, which is 2. And that is definitely rational. And so while we haven't given an example that we know for sure A is irrational and B is irrational, we've kind of come up with an airtight plan here, I guess, right? We try square root of 2 to the square root of 2. If it's rational, we're done, everything's good. If it's not rational, then we'll do square root of 2 to the square root of 2, all raised to the square root of 2. And then we'll have two irrational numbers such that A to the B is rational. So in either case, we're done, we have it, and so this is one way to show existence. This would be something called, it's actually slightly constructive because we know it's one of two options, but sometimes existence proofs are totally non-constructive and there are no examples. Those things are a little bit weird. We probably won't get to them in this class. Feel free to ask me that question during office hours or something like that. Maybe I'll try and find an example of a non-constructive existence proof. But that's it for this video. Hope you enjoyed it. In the next video, we'll talk about proof by contradiction, and that'll be fun. See you then.